America's biggest reservoir is shrinking before the eyes of millions, leaving behind a massive white scar that stretches across canyon walls once hidden beneath deep blue water. The pale mineral ring surrounding Lake Mead has become one of the most recognizable images of the American Southwest, marking the steady retreat of a reservoir that for generations represented stability, abundance, and engineering triumph. Every foot of declining water reveals another chapter in a crisis that has been building for decades rather than years. Every new projection raises another difficult question. Just how much farther can the reservoir fall? At what point does one of the nation's most important water supplies reach limits that engineering alone cannot overcome? And why has a multi-billion-gallon reservoir continued shrinking despite years of conservation efforts and increasingly urgent warnings? Lake Mead remains the largest reservoir in the United States by storage capacity. Created by Hoover Dam during the depths of the Great Depression, it transformed one of North America's most unpredictable rivers into a controlled source of drinking water, irrigation, flood protection, and hydroelectric power. For generations, the reservoir became a symbol of American infrastructure, supporting explosive growth across deserts that otherwise could never have sustained millions of residents. Today, that same reservoir stands as one of the clearest demonstrations of the mounting pressures facing the Colorado River basin. Water levels have fallen dramatically since the turn of the century, exposing rocky shorelines, abandoned boat ramps, and the striking white bathtub ring that circles the reservoir. The visual change alone tells an extraordinary story, but the numbers behind it are even more significant. Since the year 2000, Lake Mead has dropped by approximately 160 feet, or nearly 49 meters. During its highest recorded storage in the early 1980s, the reservoir approached its maximum capacity of about 26.1 million acre-feet of water. Today, it contains only about 8.3 million acre-feet, leaving it roughly 30% full. The enormous difference represents one of the most substantial declines ever recorded at the reservoir since Hoover Dam first began impounding water during the 1930s. The consequences extend far beyond the shoreline. Between approximately 25 million and 40 million people depend directly or indirectly upon the Colorado River system supplied through Lake Mead. Major metropolitan areas across the American Southwest receive drinking water from this network, while vast agricultural regions depend upon it to produce vegetables, fruits, forage crops, and other essential commodities. Hoover Dam also continues generating hydroelectric power that supports electrical grids across several states. For decades, Hoover Dam fulfilled exactly those purposes. At full reservoir capacity, its hydroelectric facilities generated approximately 4 billion kilowatt-hours of electricity each year, supplying enough energy for well over 1 million homes. Equally important, Lake Mead became a dependable reserve that buffered the Southwest against temporary droughts, allowing water managers to smooth out fluctuations that naturally occurred from one season to another. The system functioned effectively because it was designed around expectations that the Colorado River would continue providing sufficient water year after year. Later research painted a very different picture. Long-term scientific reconstructions using tree rings, historical records, and expanded hydrological observations indicate that the Colorado River's average natural flow over many centuries has been considerably lower than planners believed during the early 20th century. Instead of consistently producing 16.5 million acre-feet annually, long-term averages appear closer to approximately 13.5 million acre-feet. Conditions since the beginning of the 21st century have become even more restrictive. Since the year 2000, average annual river flow has dropped closer to 12 million acre-feet. The difference may appear modest when viewed as individual numbers, but over many years, it creates an enormous cumulative deficit between legally promised water and the amount nature actually delivers. Every year that water users withdraw more than the river naturally provides, reservoirs compensate by releasing stored water accumulated during previous decades. Lake Mead effectively became the region's savings account, gradually making up the difference between supply and demand. Savings accounts eventually become depleted when withdrawals consistently exceed deposits. That imbalance explains much of Lake Mead's long decline. The reservoir has not simply experienced one exceptionally dry season or a single unfortunate year. Instead, it has absorbed the effects of more than 2 decades during which inflows repeatedly failed to match legal commitments and actual consumption. Climate conditions have amplified the problem. The American Southwest is currently experiencing one of the most prolonged dry periods identified in modern scientific research. Studies examining tree ring records indicate that the ongoing drought ranks among the most severe in at least 1,200 years. Unlike many earlier droughts reconstructed from historical evidence, the current event is unfolding in a climate that is significantly warmer than previous centuries. Higher temperatures influence rivers in multiple ways. Snow accumulating across the Rocky Mountains melts earlier in the year, changing runoff timing. Increased evaporation removes more moisture from reservoirs and soils. Vegetation consumes additional water during longer growing seasons. Less snow survives into late spring, reducing the sustained stream flow that historically replenished reservoirs throughout summer. Researchers estimate that rising temperatures account for roughly half of the Colorado River's decline since the year 2000, while natural drought variability explains much of the remainder. Together, these factors have steadily reduced the amount of water reaching Lake Powell and Lake Mead. The effects become especially apparent when examining the reservoir's elevation rather than simply its storage volume. Lake Mead's management revolves around specific water elevations that trigger increasingly significant operational changes. These thresholds determine when mandatory conservation measures begin, when hydroelectric production becomes less efficient, and when increasingly serious emergency planning must be implemented. One of the first major benchmarks occurs when Lake Mead falls below an elevation of 1,075 feet, or approximately 328 meters, above sea level. Crossing this threshold activates mandatory shortage declarations that reduce water deliveries to certain users under previously negotiated agreements. As water continues falling, additional consequences emerge. By approximately 1,035 feet, or around 315 meters, Hoover Dam loses about 70% of its electricity generating capability because most turbines no longer operate efficiently under reduced hydraulic pressure. Lower water levels mean less force pushing water through the generating units, significantly reducing electrical production even while water continues flowing downstream. If the reservoir reaches approximately 950 feet, or nearly 290 meters, hydroelectric generation effectively stops. Water could still pass through the dam, but the turbines would no longer function as intended. An even more consequential threshold lies farther below. Dead pool occurs at approximately 895 feet, or about 273 meters, above sea level. At that elevation, water can no longer flow through Hoover Dam by gravity alone. Downstream deliveries supporting cities, farms, tribal communities, and Mexico would effectively cease unless alternative pumping systems existed. Dead pool represents one of the most closely monitored elevations in American water management because reaching it would fundamentally alter operations throughout the lower Colorado River basin. Although Lake Mead remains above that level today, recent projections illustrate why concern continues growing. The year 2026 brought another disappointing snow season across the Rocky Mountains, where much of the Colorado River originates. Snowpack serves as the natural reservoir feeding rivers throughout spring and summer. When winter snowfall falls well below average, downstream reservoirs receive substantially less runoff during the following months. Federal water managers responded by reducing releases from Lake Powell into Lake Mead by approximately 1.48 million acre-feet. The decision aimed to preserve sufficient water behind Glen Canyon Dam, preventing equally serious operational problems farther upstream. Protecting one reservoir, however, inevitably affected the other. With reduced inflows arriving from Lake Powell, Lake Mead faced accelerated declines despite ongoing conservation efforts across multiple states. Government projections indicated that reservoir elevations could approach approximately 1,021 feet, or about 311 meters, during the summer of the year 2027, falling below previous historic lows if projected conditions materialize. The forecast reflects more than seasonal weather. It illustrates the increasingly difficult balancing act confronting water managers attempting to preserve two interconnected reservoirs while overall river supplies continue shrinking. For most communities supplied by Lake Mead, declining water levels represent an increasingly difficult challenge. For southern Nevada, they also became a direct engineering problem, requiring a solution long before the reservoir approached its lowest operating levels. Rather than waiting until water shortages became an immediate emergency, the region began preparing for conditions that once seemed almost unimaginable. The result was one of the most ambitious water infrastructure projects ever constructed beneath an existing reservoir, a project costing approximately $1.5 billion that was designed for a future in which Lake Mead continues to shrink. Unlike many other cities drawing water from the Colorado River, Las Vegas relies on a relatively small allocation of the river's total supply. Yet nearly all of southern Nevada's drinking water comes from Lake Mead. As reservoir levels continued declining after the beginning of the 21st century, engineers recognized that the existing intake structures, which had functioned reliably for decades, were becoming increasingly vulnerable. Water does not simply enter a city's treatment system through a pipe placed anywhere along the shoreline. Intake structures are carefully positioned at specific elevations beneath the lake so they remain submerged under expected operating conditions. As Lake Mead fell year after year, the highest intake structures gradually became exposed or approached elevations where reliable operation could no longer be guaranteed. Southern Nevada originally relied on two intake tunnels constructed decades apart. The first intake, completed during the 1970s, was designed for a reservoir that engineers expected would remain relatively full throughout its lifetime. It performed exactly as intended for many years. However, as Lake Mead continued dropping, planners realized the intake would eventually rise above the water surface if the decline continued. A second intake was later constructed at a lower elevation to provide additional security. While it significantly improved reliability, projections showed that prolonged drought could eventually threaten that intake as well. Water managers therefore faced an uncomfortable reality. The city needed an entirely new way to reach the remaining water, even if Lake Mead continued falling far below levels once considered extraordinarily unlikely. The solution would require going deeper than any previous intake tunnel ever built at the reservoir. Planning alone demanded years of geological surveys, underwater mapping, drilling investigations, and structural analysis. Engineers were not simply installing another pipeline. They were attempting to excavate beneath one of the largest reservoirs in the United States while maintaining the integrity of Hoover Dam's surrounding geology and ensuring the existing water supply remained uninterrupted throughout construction. The project centered on what became known as the third intake, a tunnel extending beneath the floor of Lake Mead to reach water at a dramatically lower elevation than either of its predecessors. Its location was selected specifically because it would remain usable even under reservoir conditions, approaching the most severe operating scenarios envisioned by federal planners. Constructing that tunnel presented challenges unlike conventional underground excavation. Unlike tunnels driven through dry mountainsides, this one had to be excavated beneath an active reservoir containing millions of acre-feet of water, exerting enormous pressure on the surrounding rock. Any significant failure during excavation could have allowed water to enter the tunnel under tremendous force, placing workers and equipment at immediate risk. Engineers therefore relied upon one of the world's largest tunnel boring machines ever assembled for a municipal water project. The massive machine slowly advanced through extremely hard volcanic rock beneath the reservoir, cutting a circular path while simultaneously installing concrete lining segments behind it. Every forward movement required extraordinary precision because even small alignment errors could affect the tunnel's ability to connect with its final intake location. The The boring machine itself became an engineering achievement. Measuring hundreds of feet in overall operating length and weighing thousands of tons, it functioned as a mobile underground factory. Rotating cutter heads fractured solid rock, while conveyor systems removed excavated material. Hydraulic systems supported the surrounding tunnel walls until permanent concrete segments locked together into a finished structure capable of withstanding immense external pressure. Progress remained deliberately slow. Every section required constant monitoring for rock stability, groundwater intrusion, equipment performance, and alignment accuracy. Engineers continuously measured the tunnel's position to ensure it remained exactly where design specifications required. Unlike surface construction, underground corrections become increasingly difficult once excavation advances. Conditions beneath Lake Mead added another layer of complexity. The surrounding geology included fractured volcanic formations, varying rock strengths, and zones requiring different excavation techniques. Construction crews adapted continuously as the boring machine encountered changing geological conditions along its route. Perhaps the most technically demanding portion of the project came at the intake itself. Instead of draining the reservoir to build the connection, engineers developed methods allowing the intake structure to be completed while remaining beneath deep water. Specialized techniques isolated critical construction areas despite the surrounding hydraulic pressure. The operation required careful sequencing because mistakes could have jeopardized years of work already completed underground. The completed intake reaches water at approximately 875 feet, or about 267 meters above sea level. That number carries enormous significance. Federal planners define dead pool at roughly 895 feet, or approximately 273 meters. Below that elevation, water can no longer move through Hoover Dam using gravity alone. In practical terms, downstream deliveries through the dam would effectively stop because the reservoir surface would no longer stand high enough to push water through the existing outlet system. The third intake changes that equation for southern Nevada. Because its intake opening sits approximately 20 feet, or about 6 meters below dead pool, Las Vegas retains the ability to access water that still remains inside Lake Mead, even after Hoover Dam loses the ability to release water naturally downstream. The reservoir may no longer function normally for the rest of the lower Colorado River system, yet southern Nevada would still possess physical access to the remaining stored water. That capability alone, however, would accomplish little without another equally important piece of infrastructure. As reservoir elevations continue declining, lower water levels reduce the natural pressure available to move water uphill toward treatment facilities. Engineers therefore paired the third intake with a low lake level pumping station, another massive construction effort designed specifically for extreme reservoir conditions. The pumping station contains enormous vertical pumps capable of lifting water from the deep intake tunnel into southern Nevada's treatment and distribution network. Each pump was designed to operate under conditions far outside those anticipated when Hoover Dam and the original intake systems were built. The scale of the facility reflects the importance of its mission. The pumping equipment is capable of moving hundreds of millions of gallons of water each day, ensuring that municipal supplies remain available even if reservoir elevations continue approaching historically unprecedented lows. Viewed together, the third intake and the low lake level pumping station represent far more than replacement infrastructure. They effectively redesigned the region's water access system around the assumption that Lake Mead may never return permanently to the elevations common during much of the 20th century. The investment also reflects a broader shift in long-term planning across the Southwest. Earlier generations designed reservoirs around historical river conditions that appeared dependable. Modern engineers increasingly design infrastructure capable of functioning under scenarios once treated as remote possibilities. Southern Nevada reinforced that engineering investment with aggressive conservation efforts. Despite adding more than 800,000 residents over recent decades, the region reduced per capita water use by approximately 55%. Decorative grass covering roughly 250 million square feet, or approximately 23 million square meters, has been removed, saving an estimated 203 billion gallons, or nearly 768 billion liters of water. Indoor water conservation became equally important. Nearly all water used inside homes and businesses is collected, treated, and returned to Lake Mead, allowing southern Nevada to receive return flow credits under Colorado River accounting rules. Water used outdoors, by contrast, generally does not return because it evaporates or is absorbed into landscaping. These combined measures mean Las Vegas consumes substantially less Colorado River water today than its population growth alone would suggest. Conservation has slowed demand growth, while engineering has protected physical access to the remaining supply. Elsewhere, efforts are also underway to preserve another critical function of Hoover Dam. The Bureau of Reclamation has begun installing new, wide head turbines capable of generating electricity under lower reservoir conditions than the original equipment. These upgraded turbines are intended to continue producing hydropower down to approximately 950 feet, or around 290 meters, extending electrical generation during periods when older turbines would become increasingly ineffective. Like the third intake, however, the upgraded turbines do not create additional water. They merely allow existing infrastructure to continue operating under more difficult conditions. That distinction remains central to the broader Colorado River crisis. Engineering can extend operational limits. It can maintain access to lower water levels. It can improve pumping efficiency, modernize turbines, strengthen infrastructure, and provide additional flexibility during prolonged drought. Engineering cannot increase snowfall across the Rocky Mountains. Engineering cannot reverse evaporation intensified by higher temperatures. Engineering cannot permanently compensate for a river that consistently delivers less water than legal agreements allocate. Agriculture still accounts for roughly 70% of all Colorado River water use. Urban conservation has achieved remarkable reductions in several metropolitan areas, yet municipal savings alone cannot eliminate the structural imbalance between supply and demand. The river continues producing substantially less water than 20th century allocation agreements anticipated. Negotiations among the 7 basin states therefore remain as important as any construction project. Existing operating guidelines expire at the end of 2026, yet long-term agreements balancing shrinking supplies against competing demands remain unresolved. Every additional year without durable consensus increases uncertainty for cities, irrigation districts, tribal nations, industries, and ecosystems dependent upon the Colorado River. Lake Mead's white bathtub ring has become an unmistakable reminder of those realities. It records every year in which withdrawals exceeded replenishment, every season of disappointing snowpack, and every consequence of allocating more water than nature consistently provides.